Hello, and welcome to example 1.4.4. We are going to solve the initial value problem, f double prime minus 4f prime plus 4f equals 0, with initial conditions f of 1 equals 1 and f prime of 1 equals 1. So this is a constant coefficient, second-order linear homogeneous ODE. So let's solve the ODE part first by looking at the characteristic equation. The characteristic equation is lambda squared minus 4 lambda plus 4 equals 0. So let's find its roots. We factor, hopefully we see the factoring immediately. Lambda squared minus 4 lambda plus 4 is equal to lambda minus 2 squared. If you don't see the factoring immediately, you can always use the quadratic formula. So what are my solutions? Well, there is only the repeated real root lambda equals 2 here. So I know, having gone through the lecture notes already, that I should look for f in the form f of x equals c1 times e to the 2x plus c2 times x e to the 2x, where I have to figure out c1 and c2 from my initial conditions. This extra term x e to the 2x is, of course, characteristic of a repeated real root. Let's take a moment and calculate f prime here, because I'm going to have to deal with this f prime of 1 equals 1 initial condition. So I have f prime of x is 2c1 e to the 2x, and then I do a product rule on that second term in f. I get c2 e to the 2x plus 2c2 x e to the 2x. I always like to find my f prime separately before I start playing with initial conditions, especially here when I'm going to have a product rule and just more terms in f prime. So let's go forth into the initial conditions. I want to use 1 is equal to f of 1, and that means f of 1 has to be c1 times e to the 2 times 1 plus c2 times 1 times e to the 2 times 1, and that simplifies to c1 e squared plus c2 e squared, still linear in c1 and c2, the square is just on the e. And then I'll look on this new slide at my first derivative initial condition. 1 is equal to f prime of 1. And that, because I diligently calculated my derivative, is 2c1 e to the 2 times 1 plus c2 e to the 2 times 1 plus 2c2 times 1 e to the 2 times 1. And that becomes 2e squared c1 plus c2e squared plus 2c2 e squared. I'll put those last two terms together. That's 2e squared c1 plus 3e squared c2. So, collecting my work from the previous slide, c1 and c2 have to satisfy the linear system. c1e squared plus c2e squared equals 1, and 2e squared c1 plus 3e squared c2 equals 1. Let's clean this up a little, maybe depending on your point of view, by pulling all those e squareds over to the right side. And I get c1 plus c2 equals e to the minus 2, and 2c1 plus 3c2 equals e to the minus 2. And maybe that's cleaner, maybe it's not, it's a matter of opinion. Now, you can solve this system either with a direct substitution argument. Say you solve for c1 equals e to the minus 2 minus c2, or you could rewrite this as a matrix vector system and do an inverse of a 2x2 matrix. I will do that quite a bit in the lecture notes when we meet these second-order problems now and rather later in boundary value problem land. And however you do it, you should get c1 equals 2e to the minus 2 and c2 equals minus e to the minus 2. And then we just conclude f of x is 2e to the minus 2 e to the 2x minus e to the minus 2x equal x e to the 2x from our form of f before. And just as with the last example, we can check this by plugging back into the differential equation and checking the initial conditions. And we should always do that because there are plenty of opportunities here for arithmetic or calculus mistakes. One of my preferences is to check the initial conditions first. So I would look at f of 1, because that's easy, it's just arithmetic and substitution. And then I would look at f prime of 1, substitute and do arithmetic, and only then would I go back to the differential equation. Just in terms of order of ease of checking it, that's the way I like to do it. But always check your ODE work. So this is our last video for week 1 that I have planned, but if there is a topic that you would like to see a short video on, you're welcome to request it, and I can always add more videos later in the week, and you can also request topics for videos next week and beyond if you're looking ahead in the lecture notes. And of course, be in touch via email and Zulip and later Kaltura.